We are discussing about heat exchangers, and we studied about different types of heat exchangers last time. Okay, so last time we did not actually solve any problem, but we studied different type of heat exchangers: parallel flow, counterflow, concentric heat exchangers. Then we have the shell and tube heat exchangers, plate type heat exchangers, cross flow heat exchangers. Okay, we studied different types of heat exchangers. Now, within the heat exchanger phenomena, what we assume is that Assalamu alaikum. كيف الحال؟ هذا what do you say؟ يوم العيد ها؟ Okay. So let's come to the topic. Okay, so we assume that there is no heat loss. We assume that the heat exchanger itself is adiabatic. Adiabatic means whatever the heat exchange is going through, it is between the two fluids. One fluid is giving heat, other fluid is accepting heat. But there is no external heat coming from somewhere, and none of the heat is rejected, okay, outside. So there is no interaction with the outside. We assume that we make it 100% adiabatic system. Perfect insulation we put around the heat exchanger. So whatever the heat exchange takes place, it's between the two fluids. It's within the heat exchanger. Okay, it's an in-house thing. Nothing outside world in contact. Okay. So if we assume this, then it becomes a bit simple for us, because the amount of heat rejected or the amount of heat supplied by the hot fluid is equal to the amount of heat accepted by the cold fluid. That's the energy balance then. There is no outside interaction in terms of the heat. So amount of heat supplied by one fluid becomes equal to the amount of heat accepted by the other fluid. As simple as that. And the amount of heat convected is also equals to that same amount, because how do you supply? Through convection. So amount of heat convection is also same. And you know, between the two fluids you have the wall. So amount of heat conducted through the wall would also be the same. It's the same amount of heat which is being transferred from one fluid to the other fluid. So amount of heat convected from one fluid to the wall is equals to the amount of heat conducted through the wall is equals to the amount of heat convected from the wall to the other fluid is equals to the amount of heat gained by the other fluid is equals to the amount of heat lost by the first fluid. So all these heats are same, because we assume that there is no interaction outside in terms of the heat. It's a perfectly adiabatic heat exchanger. No heat from outside can come into it. No heat can be lost from this to outside. Is it clear? So, so if we have the hot fluid, now we will refer as hot fluid and cold fluid. One will be supplying heat, other will be accepting heat. The one supplying heat is the hot fluid. The one accepting heat is the cold fluid. Okay, so now we're going to refer as hot and cold all the time. Okay, so Q, as per the energy balance, amount of heat supplied by the hot fluid, mc delta T. Okay, m hot, cp hot, and delta T hot. Delta T hot means T hot outlet or minus inlet, or inlet minus outlet? Inlet minus outlet, because inlet temperature would be high, and as it will be supplying heat, its temperature will drop. Inlet minus T hot outlet. Okay, so you got this thing. This thing will be equal to the amount of heat accepted by the cold fluid. So Q is equals to, also this equals to m dot C. This is m dot for the cold fluid, then CPC, and delta T. Delta T will be T cold outlet minus T and cold inlet. Because cold fluid will have low temperature in the beginning and its temperature will rise. So larger value will be at the outlet. So Tc out minus Tc in. It's clear? And this thing is equals to the actual amount of heat convected. This is equals to the actual amount of heat convected between the two fluids, which is UA delta T. Right? And UA delta T, but this delta T will be delta T ln log mean. Because the hot fluid temperature is also changing and the cold fluid temperature is also changing, so we'll take the log mean temperature difference. Okay? So these three equations becomes the fundamental equations here. These three equations becomes the fundamental equations here. Okay? So if you see here in the first two equations, it's just dependent upon the fluid properties and the temperatures. So the first two equations does not tell you how big is the heat exchanger. How big means what is the area of heat transfer. But there is no area of heat transfer in these two equations. Right? The fluid properties and the temperatures. But the third equation, this equation has area. So this equation will be one of the fundamental equation if you want to design a heat exchanger, if you want to know what would be the size of heat exchanger. So will your heat exchanger be this much or that much? So it's a fundamental question. How big is your heat exchanger? So we need area. How much is the heat transfer area? So this equation, the last one, UA delta T, will be very significant for that because it involves area. Okay, but the other two equations, they are significant from the fluid point of view. They are significant from the fluid point of view. This is significant from the heat transfer area point of view. Okay, but all these three Q's are same because we assume there is no external influence. It's adiabatic. Is this concept clear so far or not? Any question? Okay, so what we do here is that this is m dot. M dot, what's the unit of m dot?
kg per second.
Kg per second. This is Cp. What's the unit of Cp? Kilojoule
Kilojoule per kilogram Kelvin.
per kg Kelvin. Right? So if I combine the two, so they are in multiplication, kg will cancel, right?
Okay.
And kilojoule per second, watt, that becomes kilowatt. So it becomes what? Kilowatt per Kelvin, or watt per Kelvin, depends upon what unit you're using. So we combine these two things together, okay? And we say this is heat capacity rate, capital C. Capital CH, this will be capital CC, heat capacity rate. Okay. Now these heat capacity rates this heat capacity rate is a very fundamental parameter based on which you are going to make decisions. Based on which you are going to make decisions. Okay, now in the last equation, Q is equals to UA delta T. UA was something which we discussed in detail last time. Remember, we discussed this equation. 1 UA is equals to 1 upon outside heat convection coefficient, then the fouling, then the wall resistance, and another fouling. So this is 1 upon UA. Okay, so that deals with the UA. So now you know how to deal with UA. Let's talk about delta TLM. Delta TLM is another important parameter here. Okay. Now delta TLM has one simple formula, and we discussed that formula before.
Yes.
We discussed that formula before, and that formula was delta T inlet minus delta T outlet upon ln delta T inlet upon delta T outlet. Right? This is delta T ln, log mean temperature difference.
No, it's cold inlet.
Hmm?
Delta T inlet is hot inlet.
We're going to discuss this is most important parameter here. That what is delta Ti, what is delta To? It is going to change from parallel flow to the counter flow. From what kind of heat exchanger, this delta Ti and delta T naught will change. So this is important thing. So we're going to discuss this. Okay. So you remember parallel flow and counter flow heat exchangers. So let's talk about double pipe heat exchanger. If it is double pipe heat exchanger, the concentric tube, one tube inside the other tube. Okay. So if it is okay, let's say this is the length of the heat exchanger. Okay, this is the length of the heat exchanger. So here is your heat exchanger. This is outer pipe. Inside you have inner pipe. Okay. Across the length of the heat exchanger, in parallel flow, both the hot fluid inlet and cold fluid inlet enters at the same point, right? That's parallel flow. Then they move parallel.
Yes.
Right? So they both enter from the same point and then move parallel. So if I put this as temperature axis, and this is the length of the heat exchanger, and this is, let's say, inlet, or we can say one end of the heat exchanger, and this is, I can say, outlet, or instead of saying inlet and outlet, let's say this is 1, this is 2. So if this is my length of the heat exchanger, double pipe heat exchanger, or one pipe, another pipe inside. So 1 is this, 2 is this. So I'm entering both the hot and cold fluid from 1, and if it is parallel flow, they both will move parallel, will have heat transfer, and they both will exit at 2, right? So the highest temperature will be the temperature of the hot fluid inlet, and the lowest temperature will be the temperature of the cold fluid inlet, because after that the hot fluid temperature will drop and cold fluid temperature will rise as the heat transfer continues, right? So we'll have the temperature of the hot fluid. Let's say this is the temperature of the hot fluid inlet, and the lowest will be the temperature of the cold fluid inlet. Then as both the fluids continue to flow in the heat exchanger, the hot fluid temperature will drop and the cold fluid temperature will rise. Okay? So, but at any time for heat transfer to take place, this must be remembered that the temperature of the hot fluid must be higher than the temperature of the cold fluid at any point, at any section. Temperature of the hot fluid must be greater than temperature of the cold fluid, otherwise there will be no heat transfer. Okay? So this temperature difference will keep on dropping, but will never become 0. Because if it becomes 0, then there is no heat transfer. Okay? So it becomes, keep on very close like this. Just like this. This is the temperature distribution in case of parallel flow heat exchanger. See here, temperature of the hot fluid enters, keeps on dropping, temperature of the cold fluid from the enter, and keep on rising. This 1 is at one end, 2 is the other end. Okay? This figure is important for the short questions point of view. I can ask you to draw the temperature curve, the temperature variation for parallel flow. And these things are not important that you write DTH, DQ, DTC, but the main parameters, T hot inlet, T hot outlet, T cold outlet, T cold inlet, delta T. Okay? This thing is important. And the most important thing,
Arrows.
arrows. So you see here, there is arrow here, arrow here. You mess up with the arrow, you're going to pay for it. Arrows are expensive. They're going to cost you marks. Arrows. Okay, so is it clear? This is how the temperature distribution will be. Now when we need to find delta T Lm for the parallel flow, delta T I, or let's say here instead of delta T I, let's say delta T1, delta T2, delta T1, delta T2. So delta T1 will be the temperature difference at the inlet, at one end. Instead of saying inlet, I'll say at one.
THN minus TH.
So it will be THI minus TCI, right? So delta T1 will be what? THI minus TCI. What about delta T2 at the other end?
THO
Okay.
minus TCO.
No, THO minus TCO. Okay? So delta T2 will be THO minus TCO.
Okay.
Is it clear or not?
Yes.
If you know hot inlet, hot outlet, cold inlet, cold outlet, you can find what is delta T1, what is delta T2. If you know what is delta T1, delta T2, you can find what is delta TLM. This is how log mean temperature difference is determined. Why do we need log mean temperature difference? Because if we know log mean temperature difference, then we can use this equation. And this equation is fundamental for designing because it involves area. And this is one major parameter in analysis. How big is your heat exchanger? Is it as big as the size of this room, or is it as small as it can fit in my hand? Because bigger the heat exchanger, larger the material required. Again, everything goes back to economics. Larger will be the cost. Is it clear? So we have delta T1, delta T2, and this is how it's done in parallel flow heat exchanger. So in parallel flow heat exchanger, delta T1 is equal to THI minus TCI, delta T2 is equal to THO minus TCO. These formulas will not be given to you in the exam.
What?
These formulas will not be given to you in the exam. I need something to cut marks. You guys are doing very good, and it's
Not me.
really?
Yes.
Okay. And okay, so now you know that where I will cut marks, so you will remember it. Is it clear or not? Is for the parallel flow, is it clear or not? Parallel flow, one condition. If I ask you, now listen this carefully. If I ask you to draw the temperature profile and somebody draw it like this,
0.
negative, not 0. He's crossing the temperature of the cold fluid above the hot fluid. Hot fluid temperature must be higher than cold fluid at any condition, at any cross section, at all places. Otherwise, heat transfer, then it's going to be the opposite case. The cold fluid will be transferring heat to the hot, right? So if anybody do like this, so say inna lillahi wa inna ilaihi. Okay, so this thing I hope it's clear for parallel flow. Now let's talk about, oh, it's a mistake here. It's written cross flow, but it is counter flow. So please do correct it. It's written cross flow here, but it's counter flow. But we discussed the parallel flow, right? Now we're going to discuss the counter flow.
Then
The cross flow we're not going to discuss like that, but it's by mistake written here, cross flow. It's counter flow. Now, in case of the counter flow heat exchanger, this is my heat exchanger, double pipe, let's say. So the hot fluid will enter from one end, let's say from 1, but the cold fluid will not enter from 1. Because it is counter flow, cold fluid will enter from the other end,
from 2.
from 2. And then the both will move counter each other, and hot will exit from 2 and cold will exit from 1. Is it clear? So the temperature profile will be different. Hot fluid would remain the same. Hot fluid was like this. Okay? So So THI to THO. That would remain the same. But cold fluid will be switched. So now the cold entrance inlet is not here at 1. It's on the opposite end here. Okay. So this is TCI now. And then it will move up. Okay. So it will when it moves up like this. And it exits here. So here it will be TCO. And arrow very important. So in case of the counterflow heat exchange, the temperature distribution throughout the length of the heat exchanger is like this. Instead of this, it will be like this. Where cold inlet is here, this is the cold inlet here, this is the cold outlet here. This is the hot outlet, this is the hot inlet. So arrows are important to know that where is the inlet, where is the outlet. How the flow is moving. Is it moving from this end to that end or this end to that end? Because this is important for parallel and counterflow. Is it clear? Now let's talk about delta TLM for counterflow. Delta TLM for counterflow, same formula, but what about delta T1? Previous case, delta T1 was T hot inlet minus T cold inlet.
So T hot inlet minus T cold outlet.
T cold outlet. Now delta T1 is different. Okay, so now it will be T hot inlet minus T cold outlet. That will be delta T1. What about delta T2? Previously it was T hot outlet minus T cold outlet. Now it is T hot outlet minus
T cold inlet.
T cold inlet. Delta T LM formula would remain the same, but within delta T LM there is delta T1 and delta T2. The formulas for delta T1 and delta T2 will change from parallel to counterflow. Is it clear or not?
Yes.
But in any case, if you see here, temperature of the hot fluid is higher than the temperature of the cold fluid. This curve is below this curve. So if somebody do like this, big mistake. Is it clear?
Yes.
So that's about finding delta TLM for parallel flow as well as for counterflow. Is there anything that you do not understand in here so far? Now, there are now one very fundamental question arises: what is the importance of parallel flow and counterflow? Where will I use parallel flow? Where will I use counterflow? I need to exchange heat between two fluids. I have two options. I can use a parallel flow heat exchanger, I can use a counterflow. Where should I use parallel flow? Where should I use counterflow? Both have advantages and disadvantages. Now it will be your choice which you want to use. Let's first talk about parallel flow. You see, in the parallel flow, initially the temperature difference is very high, and then the temperature difference keep on dropping. So in case of the parallel flow heat exchanger, in the initial section, there will be huge heat transfer. Because delta temperature difference is very high, so larger heat transfer will occur in the earlier portion. If you want very quick heat transfer to take place in very small space, then you will prefer to go for parallel flow heat exchanger. Because in case of the counterflow heat exchanger, if you see, there is not much change in delta T from inlet to outlet. From one section to the other section, there is not much change in delta T. So the amount of heat transfer will be almost, it's like averaged in case of the counterflow. But in case of parallel flow, in the earlier section, there is a huge heat transfer, and in the later section, there is very little heat transfer. So if you want heat transfer to take place most quickly, then it's preferable to go for parallel flow rather than going for counterflow. So you get the advantage of parallel flow heat exchanger, okay? And you get the limitation for counterflow. The advantage of parallel flow is a limitation for counterflow. Now let's talk the other way around. If you see here, the amount of heat transfer by the hot fluid, the amount of heat rejected by the hot fluid is equals to the amount of heat accepted by the cold fluid. Okay? But in any case, T hot outlet must be greater than T cold outlet for the case of parallel flow. So in case of parallel flow, your T cold outlet is limited. It cannot rise above T hot outlet. So somehow you are limiting the cold fluid temperature to rise. If you are limiting the cold fluid temperature to rise, then you are limiting the heat transfer that will take place. So the amount of heat transfer will get limited. But in case of the counterflow, if you see here, in case of the counterflow, there is possibility that the cold fluid temperature becomes higher than the hot fluid temperature. Okay, so suppose it is like this. Okay, so if I draw, so the hot fluid is here, temperature cold fluid can go above temperature hot fluid, because this is the nature of flow, opposite. At any section, temperature of hot fluid is higher than temperature of the cold fluid. But now we are not limiting temperature of cold fluid by the temperature of hot fluid outlet. So larger heat transfer is possible in case of counterflow. In case of counterflow, larger heat transfer is possible. In case of parallel flow, less heat transfer is possible. But very quick heat transfer is possible in case of parallel flow. The heat transfer will not be as quick in case of counterflow. So let me give you in physical terms. If I have that much space and I need huge heat transfer to take place in this much space, then I will say, okay, I will go for parallel flow because I need huge heat transfer and I have a limited space. I need a kind of heat exchanger which does quick heat exchange. It's about quickness. But if it is not about quickness, okay, I don't have issue of the space. I have that much space. Now my importance is not quickness. My importance is amount, how much heat transfer takes place, total. Then in that case, counterflow is better, because in counterflow, the total amount of heat transfer that takes place will be larger than the total amount of heat transfer that will take place in the parallel flow. If it matters about the quickness, then parallel flow is better. But parallel flow, it will transfer heat very quick, but the amount of heat transfer will be less compared to the total amount of heat transfer will be less compared to the heat transfer by the counterflow. Do you understand the difference or not? They have advantages, they have limitations. The limitation for the parallel flow is that the cold outlet temperature is limited by the hot outlet temperature. It cannot rise above that. So if you are limiting delta T here, so the Q is limited. If Q gets limited, automatically these three Qs are same. So the amount of heat transfer gets limited. In case of counterflow, cold outlet temperature can become higher than T hot outlet. So you are now not limiting this thing. If you are not limiting this thing, so this thing is larger value, so larger heat transfer can take place. Okay. So these points are important. These two conditions are important, could be asked in the short question. What is the limitation of parallel flow? What is the advantage of parallel flow? What is the limitation of counterflow? What is the advantage of counterflow? Is it clear?
Yes.
Could be 2 marks short questions. As simple as that. Advantage and limitation of parallel flow, counterflow. Is there anything that you do not understand so far? So it's written here, advantages of counterflow, advantages of parallel flow. The same thing which I have explained to you. Okay. And you know that the profiles, temperature profiles are important, could be asked. If you forget to put the arrow, then you will pay the price. Okay. Now let's talk about special cases. Special cases are if we have a phase change take place. So suppose you have two fluids which are transferring heat, but one of the fluid is condensing, like in the condenser. So steam goes into the condenser and it gets condensed. For condensing, what do you think? Heat is required to be supplied or heat is required to be rejected?
Rejected.
Heat is required to be
Rejected.
rejected. So the steam which is being condensed is rejecting heat. So do you think it is a hot fluid or a cold fluid?
Hot.
Hot, because it is rejecting, right? So, but for the process of condensation, do you think that there is a change in temperature throughout condensation process?
Temperature is constant.
Temperature remains constant. Condensation takes place at a constant temperature. So if the temperature is constant, so from 1 to 2, how would the line look like? It's a horizontal line. Okay. For the case of condensation, the one which is condensing, is it a hot fluid or a cold fluid? It's a hot fluid, because it is rejecting heat. Something rejecting heat is a hot fluid. Okay. So for the case of condensing, one fluid line will be like this, horizontal. The other fluid will be the cold fluid, and the cold fluid will be gaining heat, which is being rejected by the hot fluid. So its temperature will rise. So for the case of condensation, the temperature profile curve is like this. Again, important, could be asked for short questions. Okay. For the case of evaporation, switch, the fluid which is evaporating needs energy to evaporate.
And evaporating at constant.
So evaporation will take place at constant, but it is now cold fluid. It is not the hot fluid now, because it is accepting energy to evaporate. And the other will be the hot fluid, and the hot fluid will keep on going through the reduction in temperature as it keep on supplying the energy. So its profile will be like this. So that's the temperature profile for the case of evaporating liquid. Okay. Suppose, okay, let's ask another thing. Suppose I have wall in between the, okay, so on one side of the wall I have a fluid which is condensing. So its heat is rejected. On the other side of a wall I have a fluid which is evaporating. The heat rejected by the condensing fluid is being used to produce evaporation in the other fluid.
Two horizontal lines, constant heat transfer.
So how would be the temperature profile look like? Two horizontal lines. The above one will be for condenser or evaporator? Condensing. Because the one which is condensing is considered as hot because it is supplying heat. The one which is evaporating will be considered as a cold fluid because it is rejecting heat. Sorry, it is accepting heat. Is it clear? So this case is not here, but. Okay. I'm telling you, this chapter is a heavy chapter. It is involving so many concepts from the old, plus there are some new things. But this is an application-based chapter. This is what is used in industry throughout. You use heat exchangers. The most important thing, if you can design heat exchanger. Okay. So then this is the third case. If let's say if it is a counterflow and CH is equals to CC, then delta T would remain constant. It will be exactly same delta T 1 to 2 at any point. Anyways, these three are the special cases. Okay, and this page is very important. because I have material in it to bring it into short questions. Okay, so now let's move towards the first numerical. We have a counterflow concentric tube heat exchanger. So it should come in your mind that what we are talking about. Counterflow concentric tube heat exchanger is used to cool the lubricating oil for a large industrial gas turbine engine. Okay. So we have a lubricating oil, we need to cool it. So that means lubricating oil is the hot one. We need to cool it. Okay. The flow rate of the cooling water. So cooling water is used to cool it. Okay. So in the concentric tube, in one side we have the cooling water, and other side we have the lubricating fluid, and they both are moving in the counterflow direction. Okay. So the flow rate of the cooling water through the inner tube diameter is given. This is an important point. How many diameters are given for the inner tube? How many diameters are given for the inner tube?
1.
So what does that mean?
Thin wall.
Thin wall. There is no wall resistance here. If there was a wall resistance, then 2 diameters for the inner tube would be given. The 2 diameters would determine what is the wall thickness of the inner tube. But there is how many diameters given here? 1 diameter. That means inner and outer are same. Thin wall. No resistance. No resistance through the wall. Okay. So the flow rate of cooling water through the inner tube. So cooling water is where? It is in the inside inner tube or in the annulus region?
Inside.
It's the inner tube. Cooling water is through the inner tube, is 0.2 kg per second mass flow rate given of the cooling water. While the flow rate of oil through the outer annulus, flow rate of the oil through the outer annulus, D naught, 45 millimeter. Now for the case of outer annulus, D naught outer diameter is given, but here we don't need 2 diameters in any case. Why? Because we assume that the heat exchanger is adiabatic. So even if it has wall thickness 0 or have a very thick wall, it does not matter. There will not be any heat transfer from outside. It's only what is going through inside. So you have this heat exchanger. Whatever be the thickness here, it does not matter because it is adiabatic. The only matter for us is if this wall has a thickness or not, because this is how the heat transfer is occurring. Okay, but here in this case we have thin wall, just 1 diameter here. Okay, while the flow rate of the oil through the outer diameter is 45 millimeter and it is 0.1 kg per second. So mass flow rate of the oil, mass flow rate of water, the 2 things are given. Okay, inner diameter given of the pipe, outer diameter is given. The oil and water enter at temperatures of 100 and 30 degrees centigrade. Oil enters at 100, water enter at 30 degrees centigrade, respectively. How long must the tube be made if the outlet temperature of the oil is to be 60 degrees centigrade? So that's a very genuine question, that you have oil 100 degree, you want to cool it with water. Water is at 30 degree. Now, what should be the length of your heat exchanger such that the oil temperature reduces from 100 to 60? We just want the oil temperature to reduce from 100 to 60, not more than that. Because for more reduction, we need a larger heat exchanger, which will cost us more. Why to waste money? Okay. So just we need to find out what should be the length so that its temperature is dropped, oil temperature is dropped from 100 to 60 degree. So the first thing that you are going to do is, this thing will be provided to you probably in the exam, this figure, but this figure will not be provided to you in the exam. And the first thing that you have to do is draw the temperature profile. Okay, so you know that it is counterflow, so hot fluid is moving like this, cold fluid is moving like this, right? You know hot fluid inlet temperature, and you know cold fluid inlet temperature, 130 degree. You know what you want to achieve. You want to reduce the hot fluid temperature from 100 to 60 degree, but you don't know that what is the cold outlet temperature. This thing is not known, right? So now the very first question, you need properties, right? In order to solve these problems, for example here CP properties, you need properties. For properties you need the temperature, right? Which temperature shall we use to determine the properties? Let's talk about this one, hot fluid. Hot fluid inlet outlet are given,
Yes.
right? So mass flow rate is also given. What about this property? CP, we need this property from the property tables. At which temperature? So take the average temperature,
Between 60 and 100.
100 and 60. So it will be 80 degree. So at 80 degree, find out the CP of the hot fluid. Okay, and that's it. And find, once you know the CP, you will know what is the heat transfer. Okay, so unused engine oil at average 80 degree got these properties. Okay, now another important question. Let's talk about water. Okay, as you know that this Q, these Q's are same. So now if we know T hot outlet, T hot inlet, CP, m dot, so we know what is Q. So now we know for the cold side we know what is Q.
We can get CP.
Okay, we know what is Q, we know what is the mass flow rate. Out of TCO and TCI, what is we know? What is the thing that
TCI. We know TCI.
we know TCI, but we don't know what is TCO.
Yes.
So if we don't know what is TCO, so the question arises, we can use this equation to find TCO if we know what is CP. But for finding CP,
We have the
at which temperature would you find CP?
That's what we have.
Now that's the thing here. In engineering, you make engineering guesses. You make approximations. Okay, and you should have a thought process at the back, why you are doing it. Okay, so this is a heat exchanger. Heat will exchange. Okay, so do you think that the temperature of the cold fluid would rise? Of course it will rise. So one thing is very clear, that T cold outlet will be greater than 30. Okay, will be greater than 30. One thing is very clear. So that means if somebody take properties at T average 30 degree, it will be wrong. Because taking properties at T average 30 degree means you are saying that TCI and TCO are same. Right? That will be wrong. Okay, then let's talk about the other thing. You know that its temperature would be greater than 30. But you don't know how much greater. But you know one thing, it cannot be higher than 100.
Yes.
Okay? Cannot be higher than 100. So if let's say if it was 100, if TC out is 100 and TC in is 30 degree, so what will be T average?
65.
65. Okay? So you know that 65 is wrong.
Because it is bigger than 60.
Okay, so 65 is wrong because if you consider 65, average 65, that means you're saying that TC outlet is 100, which is not possible. That it cannot meet. Okay, so your value of temperature that you are going to take should be between
130.
30 and 65. 30 is wrong, 65 is wrong, in between is correct. So if somebody use 40 degree, I will consider it okay. If somebody use 50 degree, I'll consider it okay. If somebody use 60 degree to find properties, I'll consider it okay. If somebody use 30 degree, not okay. If somebody use 65 degree, not okay. If somebody use above than 65 degree, not okay. Is it clear? You need to have a reasoning why you are doing something.
Okay, why he choose 55?
Because he knows the answer, but you don't know the answer. He knows the answer, but you don't know the answer. So suppose you don't choose 35. He choose here 35 degree. Suppose you don't choose 35, you choose 45. Your answers would be a bit difficult, a bit different. But I will not consider that wrong. The logic is correct. You don't know TC outlet. We can assume a value, but that assumption should be based upon some reasoning. Is it clear?
65 years. Where we get 65?
Look, what we said is that this temperature, this property should be taken at an average temperature TCI, TC naught.
This is the average. Yeah.
This is the average.
Okay.
It can't be bigger than 60.
It can.
They should, the temperature photo can't be.
No, that was for the case of parallel flow.
Counter is-
Counter, that's the thing. That was the thing which was limiting the parallel flow case. In counter flow, it can be greater than 60 degree. But at any cross section, the temperature of hot should be higher than the temperature of the cold. Is it clear? So here they took 35 degree. Okay, taking 35 as an average means taking TC out at 40, because TC in was 30. If average is 35 means TC out was taken at 40. Okay, that's an assumption. Actually, answer will be 40. Okay, but if you don't know it, but you take any value in between the two limits, and it's okay. Your answer so might be in the 10 students in the class, all will have different answers, but all might be correct at the same time. I'll see the logic that you used. Is it clear so far? Good. So we find out what is Q. That's the first step. We found out what is Q. Then we can find out what is TC outlet. Okay? By considering approximating the properties. Okay? And so we'll find out what is TC outlet, and TC outlet comes out to be how much? 40.2. So now they say that since it is 40.2, our approximation was correct. It's okay, their approximation was correct. Actually, that is the reason many times we need iteration. But in the exam, I will not ask you to iterate. Suppose you take TC average, instead here they took 35. Suppose you take 55. It's still okay. But your answer will come close to 40, maybe around 42, maybe around 38, maybe around something like that. So now you know that your approximation was hugely wrong compared to that. So you go back, and this time you use the new TC out value that you find. Take that for finding the average and property. Then solve it again. Eventually a time will come, so you solve it again, then if it is again different, then solve it again. So eventually a time will come that TC outlet would be exactly the same which you are approximating in the beginning. That's why iteration is needed. The only thing that, since you are not solving on computer, since you are solving on paper and pen, and you do not have infinite time, so I will not ask you to iterate. The things that I will see, did you choose the temperature based on certain logic? And secondly, I might ask you, do you think iteration is needed? So if you find out that your T outlet is very far away from your approximation, then you will only say, yes, I think iteration is needed. That's it. Okay? So I will not ask you to iterate again. I will not ask you to resolve the problem again. But just tell, do you think resolving is needed or not? Suppose somebody actually took 35 and his value is coming 40.2, so he will say no, iteration is not needed because my value is approximately the same as the value I assumed. Okay, is it clear? So we got TC out. Now we know what is TC out. Okay, we know what is Q. So now let's come. What was the objective? Objective was to find the length. But for finding the length, you have to use this formula. Q is equals to UA delta TLM. But for finding delta TLM, you must know T hot inlet, T hot outlet, T cold inlet, T cold outlet. That's why we first find T cold outlet. Otherwise, we cannot find delta TLM.
We found T cold outlet to go to the table and find CB code, and then solve for T outlet, right?
Yeah. We assumed first T cold outlet, find out CP,
Assume
then calculated T cold outlet again. Okay. So is it clear? So now we need to find out this area. Okay. So Q is equals to UA delta TLM. Now delta TLM, what will be that? It will be delta T1 minus delta T2 over ln delta T1 upon delta T2. Okay. Since you have already drawn this, so this is delta T1, this is delta T2. So it should not be an issue for you. You know what is T hot out, T hot in minus T cold out. T hot out minus T cold in. Since you have already drawn this, so you know what is delta T1, you know what is delta T2, you can find what is delta TLM. So this is done here. T hot in minus T cold out, T hot out minus T cold in. Upon ln delta T1 divided by delta T2. Same thing. And it comes out to be 43.2. So now we know what is delta TLM. Okay. And we know what is Q. Okay. So now if we find what is UA, we will find UA. Okay. So if we know what is UA, we can actually find out what is the area. Now we know that for the formula of UA, what is the formula of UA? The formula of UA was this one, right? That was the formula of UA. In this case, first of all, do we have any wall thickness?
No.
So this is not there. Do we have any fouling on the outer side or inner side? Is it said anything?
No.
No fouling on the outer side, no fouling on the side. So what we are left with. Do we have any fins?
No fins.
There is no extended surface, just one pipe, another pipe. So this thing N naught will be 1, overall efficiency here will be 1, with no fins. Okay. So what we are left with? It's the same thing, 1 upon H A plus 1 upon H A. One for the cold side, one for the hot side. That's it. Okay.
Do we have H?
So now you have to go to chapter number 6 to chapter number 10 to find H's. So now you have to go,
Correlations
huh?
now? Correlations?
Correlations.
What's the
Huh? You know, that's why I was saying that if it will be good for you if you can just review some lectures before. But anyways, since everything is videoed, so you can go back. I know that if you have not, if you do not remember things from the last chapters, you will find hard to understand some of the things, but eventually you will understand when you're going to study them. So here let's so you have this formula for
You cancel the area.
area cancelled. Why? Why did he cancel area?
We need the length. We need the length.
But here in this equation, if the equation was like this, right? 1 upon UA is equals to 1 upon HA for the cold side plus 1 upon HA for the hot side. He cancelled the area. Why? Look, A cold side, A hot side
The same as
will be the same because there is no thickness. A depends upon diameter, and diameter out and in are same because there is no thickness. So automatically it will cancel. Okay? So you will find U. But once you know U, you can substitute in this equation, find A.
we find A, we don't know.
We don't know A. Do we know A?
don't the length. Yeah.
We don't know the length. Okay? So is it clear? So for this we need 1 upon Hi plus 1 upon H naught. Hi will be what? The inside fluid,
What?
inside water. Ho will be what?
For the oil.
For the oil, but oil is where? In the annulus region. We did not solve the problem for the annulus region, but I told you that I have put one homework problem in the annulus region for chapter number 8. And if you have not gone through that homework problem, you will not understand how did we find H naught.
For anniversary.
Annulus region. There are tables there for the annulus region as well.
We can use the table side.
Yeah, you will use the table, but you have to understand what it's dealing with. Anyways, the first thing in order to find H's is we need to find whether it is laminar or turbulent flow. So first thing we need to know what is the Reynolds number. So Reynolds number is 4m dot upon pi d mu. We went through this formula, 4m dot upon pi d mu. If you don't remember, you will remember it when you see it. Okay. So m dot, let's talk about the cold fluid. So the mass flow rate of the cold fluid, 4m dot upon pi d diameter and mu, we know all these properties. Find out the Reynolds number. Reynolds number comes out to be 14,050. What do you think? Do you remember it?
Turbulent because it's more than 2,000.
2,300, yes.
300? It was just 2,000.
Okay, above 2,000, okay. So anyways, so it is turbulent flow. So if it is turbulent flow, what will you do? You will go into the table, and then there were 3 formulas for turbulent flows, and you check the Prandtl number. And it was find out that the Dittus-Boiter equation will be used.
Doctor, can you give us the steps ahead?
We can give us the number. You test us on the how to get the length from the Q.
No. Anyway. So even in that you have to check whether Prandtl number was power n, whether it is heated or cooled. 0.3 or 0.4, here it is 0.4 because this is heated, water is being heated. Okay. Okay, we substitute all the values, we get the Nusselt number. After we get the Nusselt number, we get what is Hi. Just Hi. Ho is the annulus region. The thing that we did not solve in the class, but I gave you the homework problem.
Okay,
Okay.
let's do it.
Again, first thing we need to find the Reynolds number. For the inside, we know it is turbulent. For the inside fluid, cooling water. But for the outside, in the annulus region, is it laminar or is it turbulent? First thing we need to find that. So for finding that, you know the Reynolds number formula is rho Vd upon mu, right? But d is the hydraulic diameter. And I made you solve for hydraulic diameter in the class. I asked you that time that take paper and pen and solve for the hydraulic diameter, if you remember. Okay. So it was determined that the hydraulic diameter is d naught minus di. outer diameter minus inner diameter in the annulus region. So this is rho d mu. Okay. What about v? That is the velocity. But what we are given? We are given the mass flow rate. Mass flow rate of the oil is given.
Yes.
So how is mass flow rate and velocity linked together? What is the relationship of mass flow rate and velocity? You're giving every week exam of fluid mechanics, right?
AV equal to
AV, yes. But AV is not mass flow rate, it is volume flow rate. M dot is equals to rho AV. If you just say AV, this is the volume flow rate. It's not kg per second, it will be meter cube per second.
There is a formula for hydraulic diameter.
Yes.
Which is
The hydraulic diameter formula is 4 cross-section area over parameter. Now, I ask you what is the, because we need to find this u, right? Velocity. So velocity will be what? Velocity will be m dot upon rho a, right? So m dot is given, rho is given, you took out, and a will be what? M dot upon rho a. A will be the cross-section area of flow, but this is the annulus region. Yeah. So pi into d naught square minus di square by 4. So after doing this, you will find out that the Reynolds number is 56. What do you think? Laminar, turbulent? Laminar. Now then, when you have to use the table for the annulus region. The tables for the annulus region will give you the Nusselt number as a fixed value, 5.63. There was no formula, directly value taken from the table for the laminar. When you go through that table, you'll remember it. Okay, and then we find out H naught. Now, once we know H naught, we'll find out what is U. Now, once we know U, we can substitute in this formula. So now we know Q, U, delta TLM. So we'll find A. But once we know A, we still want to find length. So length will be what?
divided by dl.
Yeah.
By dl.
So your area will be pi dl. Right?
Just divided by
Diameter is known, and length you need to find. So it turns out to be, if you take 66 meter length, then it will transfer the heat, it will make it from 100 to 60 degree. If you take length less than 66 meter,
it will not become 60.
okay. If I ask the same question in exam, but I say you that somebody suggested that we take the length of a heat exchanger, a 30 meter length heat exchanger, and find out will this heat exchanger do the job or not.
Much easy.
no.
It's so you will not consider that length. You will solve the problem as it is, and you will find out that what is the length required. Then you will compare that if somebody suggests 30 meters, so do you think within 30 meter length this job will be done? No. Okay. So
Okay. If my answer is different, I say no.
okay. So, anyways.
I have a question. Why is AC is equal to the H?
Why AC is equals to AH? Good. This is a good question. Okay. So look, so you have, this is your outer pipe, this is your inner pipe. Now, as I told you, outside is complete insulation, so there is no heat transfer from the outer pipe outside. It does not matter what is the thickness here. So the only heat transfer is occurring from here to here. Okay. So now, if we have a wall thickness, then what will be the heat transfer? So this will be AI, and outer wall thickness, this will be A naught, right? Okay. So what is the formula for AI or A naught? Okay, that's the surface area we are talking about. It's basically pi dl. Okay. So for AI it will be pi dil. For A naught it will be pi d naught l. Right? But di and d naught are same here. Is there any thickness for this wall? So di is here we are using do, but that do we are considering this outer diameter, not the thickness here. That do, wherever it is written do, it is not considering this thing. It is considering the for the other pipe. For every pipe you will have a di and d naught, right? For every pipe you will have a di and d naught. Okay, but since for this inner pipe it is considered as a thin pipe, no wall thickness. Okay, and heat transfer will be occurring in this region, from the outside fluid to the inside fluid. In between you have just the wall. Okay, so this H for the cold fluid will be the H inside. This H for the hot fluid will be the H outside. Okay, so this area for the cold fluid will be the surface area of the inside tube. This area will be the surface area of the outside tube. But the surface area of the inside and outside tube are same, because the diameters are same. Because there is no wall thickness. Is it clear? Is it understandable or not? It's heavy. I know it's heavy.
Question, you need the 1 hour yourself.
No, inshallah, you will get practice and you will do it in 15 minutes.
Okay.
Okay. Is it okay? For the understanding point of view, is it clear or not? Yeah, some of the things you might have right now kept it for the future because you do not remember how we used to do things in the previous chapters. But anyways, considering that, is the theory concept everything clear or not?
Yes.